Everyone, thank you for joining the Cognitive Systems Institute Speaker Series. Today I'm happy to announce and introduce Dr. Steve Fiore, who's the director of the Cognitive Sciences Laboratory and professor with the University of Central Florida's Cognitive Sciences Program. Oops, I hear some echo in the background. Maybe mute until I finish my introduction, Steve.
Okay.
Steve's primary area of research is the interdisciplinary study of complex collaborative cognition and the understanding of how humans interact socially and with technology. Dr. Fiore has contributed to working groups for the National Academies of Science in understanding and measuring 21st century skills. As principal investigator and co-PI, he has helped to secure and manage approximately $20 million in research funding. He's the co-author of a book on accelerated expertise and is co-editor of volumes on shared cognition, macrocognition in teams, distributed training, and team cognition. He has also co-authored over 200 scholarly publications in the area of learning, memory, and problem solving on individuals and groups. Please help me welcome Steve Fiore, who will talk to us today about developing cognitive systems to support team cognition. Thanks, Steve, for being here, and I'll turn the call over to you.
Okay. Thanks for having me, and welcome everybody. I appreciate your taking the time to listen to some of what my colleagues and I have been developing over the last few years. So what I want to talk about today is first provide some background on team cognition and one of the research frameworks we've been developing to study team cognition, but then segue into some considerations of how we can use technology and this concept of cognitive computing as a way to potentially augment team cognition. And then I'll conclude with some thoughts about this approach for science and society. So first and foremost, there's an area of research in the study of teams that we've labeled team cognition. And this came out of kind of a blend of social cognitive organizational research where people started to wonder what happens to cognitive processes when people work in a team. Now, this is an old idea. Social psychology had been thinking about this for a very long time. In fact, if you go back into the original social psychology literature, you can find from papers back in the 20s, for example, Allport talking about the group's influence on association of thought. But it wasn't until the 90s where people started to take this concept a little bit more seriously within the context of looking at teams in organizations, and the overarching issue that they wanted to understand was how do cognitive processes arise in complex and dynamic interactions. But the real overarching epistemological issue we're trying to understand is how does the manifestation of cognition in teams result in a coordinated entity? That is, how does cognition produce this concept of a team, and how are people able to coordinate not only their behavior, but their knowledge? And what I want to focus on is how technology can be leveraged to augment these kinds of processes to support individual and team cognition in service of collaboration. So with that as kind of the foundation, I want to narrow it a bit into this topic of macrocognition in teams. And this is something my colleagues and I have been working on for a number of years now. And it started essentially as an interdisciplinary integration where we looked at the large and broad areas of literature that had been thinking about cognition and collaboration and tried to pull from those to develop an overarching framework to explore this issue. And a number of you may be familiar with some or all of these. So there was initially some research in situated cognition coming out of education research and the influence of the environment or context on cognition. Ed Hutchins had a lot of influence by studying cognition in the wild, and he came up with this idea of distributed cognition. But actually in schools of communication and communication research, there's a rich and robust body of knowledge, and even though they didn't necessarily call it team cognition, they were looking at things like problem solving and decision making and coming up with ways to understand and explore that. So I think it's a very important body of literature for those who'd like to study real world cognitive and collaborative processes. And more recently, out of computer-supported cooperative work and similarly computer-supported collaborative learning, this idea of group cognition has emerged. So when we developed our approach, we looked at it from those disciplines, and we took the perspective of cognitive engineering. And cognitive engineering is another one of these integrative fields where the approach is we don't want to just think about it from the standpoint of computer science or engineering, but we also want to look at it from the human standpoint and what we know about human cognition, the goal being the development of human technology systems. and we try to understand the emerging intersections of humans and technology. And within that research space, Eric Hallnagel in the UK developed his concept of macrocognition. And this was specifically called and labeled macrocognition because they wanted to distinguish and separate it from what they labeled microcognition. And microcognition was essentially what was going on within cognitive psychology, within cognitive science, where they were studying undergraduates in the laboratory, looking at essentially simple kind of problem-solving tasks, puzzles, memory. And although that research is fine for explorations and some theory development, it really wasn't informing the development of much more complex cognitive processes and how to understand cognition in the real world. So Hallnagel and colleagues within cognitive engineering, again, developed this idea of macrocognition, and he articulated these 5 important features that are necessary to call something macrocognition. So first is this idea that across natural and artificial cognitive systems, cognition is going to be distributed. They noted that cognition is not self-contained, but it's a continuance of activity, so it's a dynamic kind of process. Cognition is contextually embedded within the social environment. This cognitive activity is dynamic, it's not stagnant. And an important one is that artifacts aid in nearly every cognitive action. So these components are what they labeled as the defining features of macrocognition. And my colleagues and I worked with that from the standpoint of how can we think about this within team collaboration and team cognition. And we came up with this concept of macrocognition in teams. And this representation here is what we developed early on as a kind of a conceptualization of what we were thinking about. I'm not a graphic artist, so it's really not that sophisticated. It was the best I could do using PowerPoint. But really what the idea trying to get across here is imagine this is a 4-person team working on a problem. And the upper left-hand quadrant, you see 4 circles with these arrows, and that's supposed to represent the thinking of 4 individuals, their individual cognitive processes, as they try to understand their initial introduction to this problem. And that transitions to the upper right-hand quadrant where you see the large circle, and that's supposed to represent the group now communicating about what they know about the problem. That transitions to the lower right quadrant with the 4 individuals thinking again, and then to the lower left where you have the group. And this essentially cycles through with this individual and team kinds of cognitive processes. So this illustrates a 4-person team interacting to build knowledge and solve their problems. So in the center, you see that D to I to K, and that's meant to represent how do we go from data to information to knowledge through these kinds of iterative processes. And what this represents here is what we talked about as parallel, interdependent, and iterative nested processes as teams work to solve complex problems. So from this initial conceptualization, we developed this, what we call this macrocognitive model, to specify to greater degree these 3 theoretical elements that are the foundation for the model. So first and foremost, this is multi-level in the sense that we wanted to understand individual and team level factors. Next is this notion of internalized and externalized cognitive functions. That is, we didn't want to think about only cognition within the head. We wanted to think about cognition in the world and how that gets utilized by the team. We also incorporated time into this model. That is, we have temporal characteristics associated with the problem-solving phases. So problem-solving itself is something that shifts in phases as teams come to a better understanding of the situation they're facing, and we wanted to take that into account with our framework. So now I'll dig a little bit deeper into these specific macrocognitive functions that are part of the model. Again, these are represented on the right. And you have teams moving from internalized knowledge to team problem-solving outcomes. So first and foremost is this idea of internalized team knowledge. So this is essentially the foundation of what was the initial team cognition research. So some of you may be familiar with this idea of shared mental models, where organizational researchers had adopted the idea of Johnson Laird's notion of a mental model and recognized that indeed effective teams themselves acquire what they thought of as a shared mental model. So this is the collective knowledge held by team members, and that also evolved into what's called transactive memory systems, where they realized that, well, not all the knowledge is shared. What matters is that they have complementary knowledge and they know who knows what, so they can go to the right people to address a particular part of the problem. And with this, we talked about the idea in the context of problem solving is this notion of individual knowledge building. So you're in a unique situation, you're facing a problem that you've never faced before. How do you start building knowledge about that problem? So this is where individuals work to understand the problem on their own. So this can happen inside the head, so to speak, where they may start visualizing objects, but it's also overt actions where they're going to look to the world. They could be accessing something from their screen. They could be seeking out further information. You can be going to the literature, essentially starting to collect and analyze your own data about the problem so you can analyze it and build knowledge about the situation you're facing. That transitions to team knowledge building, where you start to work together, you share what you found, you share information, you try to transform that information into actionable knowledge. That is, you want to start thinking about what do we know and how can we just start developing solutions to understand this problem. So this can be kind of a collaborative data collection, collaborative integration of ideas, this deliberation and discussion. And I also want to note that within each one of these major macro-cognitive functions, we have subsets of processes that we have specifically operationalized for the purposes of defining and measuring what these major macro-cognitive processes are. And that's in some of the publications that are referenced in each one of these slides. So after they go to team knowledge building, they start to work on this notion of externalizing team knowledge. So that's essentially, what do they come to agree on it, or at least want to make concrete, the kinds of facts or concepts or artifacts that they think are relevant to the problem-solving situation. So these can be kind of analytic outputs, reports, graphs, charts, what have you, where they've made concrete, they've begun to reify the knowledge that they're building in such a way that they can utilize that to produce something usable for the problem-solving context. And out of that, they develop these solutions that are potentially actionable. So again, the idea here is that this is an iterative process that teams move through as they work on solving a problem. And it's not represented here, but it goes through these problem-solving phases where they first start to engage in knowledge construction to try to understand the problem. They move to what we label team problem model development. That's kind of, you can think of as defining the problem space in which they're operating. And then they move to team consensus as they narrow down what they've discussed and debated to actionable or potentially actionable solutions. And then they evaluate those ideas through a kind of argumentation process where they essentially interrogate the ideas that they've generated for the purposes of determining whether or not they truly have met the problem constraints. Are they meeting the objectives that they set out to? And they will cycle through these processes until they come to something that they believe is actionable, and they'll move to an execution phase. So that's a very rapid overview of the model. And again, these references are there if you're interested in digging a little bit deeper. But the point now is to think about this from the standpoint of cognitive computing. So these are the dimensions of the macrocognition and teams model. And what I want to talk about now is how these are potential targets for augmenting team cognition. So the idea here is, can we move from cognitive computing to team cognitive computing? So the point being that we have a theoretical base on which to build the work that's been going on in cognitive computing. So now I'm going to talk about how we can augment team cognition through team cognitive computing. So essentially, how can we leverage what's been going on with computational intelligence to support problem solving? So we need to integrate theories of team cognition with this notion of cognitive computing. And the way we encourage people to think about this is this idea of technology as a teammate. And this is really what we need to start considering for the future of problem solving. Because currently, at best, what we have is technology as a tool that supports what we do in problem solving and decision making. But what we want people to start doing is to acknowledge that as this technology is becoming smarter, we should leverage what we know about teams more generally and human behavior and human cognition and team cognition to produce technology that can actually be a teammate. So as an example now, Watson, even though it's very sophisticated, natural language processing, et cetera, I don't think anyone really thinks of Watson as a teammate just yet. There may be some kind of dyadic coordination going on, but I've never seen anyone publish where Watson is really engaging in the kinds of team behaviors that we understand from studying organizational research for a number of years now. So the idea is, can we integrate what we know about teams with cognitive computing to create technology as a teammate? And again, this is necessary to support these kinds of 21st century challenges that we're facing, the kinds of grand challenges that have been put before us. and it also extends the resources available to humanity. So we have a tremendous amount of knowledge on the internet now, and we also have a tremendous body of knowledge within teams. And with this idea of technology as a teammate, can we augment and extend that so it becomes better synthesized for the problem solving? And again, the idea being that if we can leverage technology, now humans can focus on the more cognitively complex problem elements, the kinds of things that computers are not yet able to do. So now I'm going to go into some specific examples of what I've seen within the area of loosely labeled cognitive computing. And these are kinds of impressive examples that I've come across where technology is being used that I think fit nicely within the macrocognition and teams framework. So at the top of the slide, the example here is here's a technology that supports what we would call internalized knowledge and individual knowledge building. So this is something that leverages what's known as deep dive, and it's a very impressive machine reading technology. And it's built to overcome the challenges with regard to literature-based compilations. So there's a lot of data out there. Ben Jones at Northwestern refers to this as the burden of knowledge. Essentially, the scholarly community, science and technology communities are producing more knowledge than humans can keep up with. So what this technology does is it engages in this kind of knowledge synthesis process that humans normally do. And I like this one because it's important for science and technology problems. It goes through and not only does it read the text, but it extracts data from tables and figures, what they refer to as dark data, and it synthesizes that and it produces something that can be usable to the problem solvers themselves. So this is normally something that a human would do in the knowledge building process. So I think this is a kind of next step that we can think about for cognitive computing and leverage that within the context of the macrocognition and teams model to develop internalized knowledge and to augment the individual knowledge building process. So that is, this technology, deep dive here, is something that's usable for data integration and data synthesis. The next one that I've come across recently similarly is useful for the context of internalized knowledge and individual knowledge building processes. This is the Erasmus system that came out of Georgia Tech, and it was recently published where they were talking about how to develop cognitive computing for cognitive assistance. So notice their use of the word assistance there. They're moving really towards this idea of a teammate, but they don't specifically use that term. But when I was reading this, I was thinking that this is a step in that direction. And I also like this one because what they did is used IBM's cognitive computing and the Alchemy API to support querying the knowledge space. So researchers are able to put out a query, and it diagnoses that query and separates it out into a number of possible questions, and then it searches a problem space, the literature space, and it spits out kind of a visualization of what they labeled the solution space in a technical domain. And you can see on the right-hand side the graphic that I pulled from this publication where they have what they call a concept neighborhood tree map. And essentially, those are the primary concepts that were part of this question. And in this paper, they used as a case study biomorphic design. And the point here is you have designers who don't really know anything about biology, but they want to leverage biology to solve this complex problem of biomorphic design. And in this case, they wanted to develop how is it that people can produce drinkable, usable water from salt water. And they went to, well, how is it that seabirds are able to drink water? And they went and they put that question out there. And what the Erasmus system did was go through the literature and spit out essentially a number of concepts that could help this engineer with its biomorphic design problem. So a really interesting way to distill a large body of literature for people who are not familiar with that literature. And this is an important part of complex problem solving because even though we may be expert in a particular area, we're not going to be expert in all areas, and it's not always possible to bring in team members who are experts in this area. So I thought this was another elegant way to think about individual knowledge building because here, again, the system can be a teammate. The system can start to distill a knowledge base for you, a large knowledge base, to turn it into an internalized knowledge building process where you can gather and synthesize that information. So moving on now to the externalized knowledge and the team knowledge building part of the macrocognition model. This is an example of a kind of information visualization tool. It's been around for a number of years now, and I've paid a lot of attention to information visualization because I think this kind of externalized cognition is really critical to the collaborative process. So this one is called NetDraw, and Sue Fussell, Sarah Kiesler, and their colleagues have been working on this for a number of years now. And it's an information visualization tool that supports problem solving and decision making. And it's nice because it shows not only shared access to data, but that problem solvers can use this to overcome potential decision biases. And in particular, they can see the relationships, colloquially, to connect the dots in the disparate data that they're utilizing to solve this problem. And within the context of externalized cognition, the point here is that people can use this for team building knowledge processes and share information and see the unique information that may be missing as they try to solve the problem and utilize that unique information in such a way that they can come up with better solutions. Another one that fits with this idea of externalized cognition is this collaborative sense-making tool that represents knowledge, it externalizes the knowledge, and they talk about this from the standpoint of construct representations. So basically, you take the data, you turn it into some kind of conceptual representation, you're able to articulate with this tool the relationships between the evidence and the data that you've been provided. And again, this is a way for cognitive computing to become more of a teammate through the process of knowledge object development. So right now, these are humans using these tools, but you can think about linking it to cognitive computing so the system itself can help with the representational process and to show relationship between the data and the information with which the team is working and to illustrate the relationships between the data and the evidence. So related to that is this another technology that's out there where it's part of this externalized cognition process, but it also fits with team knowledge building and the evaluation of solution outcomes. And this is a nice one because it specifically is used to support argumentation processes. So humans need a lot of help when they argue. You don't want argumentation to turn into this kind of interpersonal emotional issue. You want argumentation to focus on the intellectual aspects of the collaboration. And this was one of the technologies that's been out there that was developed to support effective argumentation. It helps orient the team members to the data, to the evidence, to the subject matter, and it helps structure their interaction so it becomes more coherent. So it removes the people from the process, so to speak, and it focuses the people on the problem, on the evidence, on the data, and their argumentation becomes more coherent. So this is something, again, that humans are doing, but it's a way forward for cognitive computing to think about how can we use this in such a way that humans are actually becoming more coherent with their argumentation processes. And within the macrocognitive model, we talk about this from the standpoint of evaluation and negotiation of alternatives, kind of regulation of their processes. So it's going to support the argumentation and the solution evaluation process. So just to wrap up, I want to provide some concluding thoughts with regard to what we think about cognitive computing and this notion of how we can use this as a form of decision aiding. So we really need to think about how we can extend and augment individual and team macrocognitive processes. So this idea of team cognitive computing, this idea of technology as a teammate. And I have a recent publication out there where we went into specific detail about what we would mean with regard to technology as a teammate and how it's possible to create hybrid human-machine teams. And the idea that I'm speaking about now is how computing models or cognitive computing models that make use of data coming from various sources, not just live data, but dark data, to create a new way of augmenting the team. So how can these very sophisticated systems out there now with artificial learning and machine learning that's been developed to sense and predict what's happening in the world actually be better integrated into team problem solving? And the purpose with this is to think about a kind of research roadmap that the cognitive computing technology can use and develop to actually pursue this from a research and development standpoint. And for that to take place, we really need better research collaborations in all areas of scholarship. We need not just computer science, not just cognitive science. We need stakeholders involved in this so we can pursue this kind of understanding that will serve complex problem solving. And the philosopher Andy Clark articulated this kind of collaboration quite well in his book Mindware that came out about 15 years ago now, where he talked about this as this form of continuous reciprocal collaboration or causation. And he says much of what matters about human intelligence is hidden not in the brain nor in the technology, but in the complex and iterated interactions and collaborations between the two. The study of these interaction spaces is not easy and depends both on new multidisciplinary alliances and new forms of modeling and analysis. The payoff, however, could be spectacular, nothing less than a new kind of cognitive collaboration involving neuroscience, physiology, social, cultural, and technological studies. So I think Andy Clark really nailed it here when he talked about what we can think about as team cognitive computing and the kinds of scholarly collaborations that are necessary. So I'll end on this slide now because this is something that I think is very important, and this is collaboration to solve the big problems. And what I mean by that is I've seen a lot of very sophisticated and technologies come out there. I see a lot of very smart people working on these technologies, but unfortunately, I don't see a lot of these smart people focusing on societal or real-world problems. So sure, it's nice if you can build a technology that's going to improve some business process, it'll help restaurants get their food faster, help restaurants get things delivered faster, or help some factory do their job better. I'm talking, though, about real-world societal problems. And what I want to encourage the community is to think about how to take on these societal challenges, to think about how you can focus on the big problems. And this was a paper that came out that I think was very important because it was in, of all places, Harvard Business Review. And they talked about solving the big problem, and they noted that forget about finding your passion. Instead, focus on finding big problems. Putting problems at the center of our decision-making changes everything. It's not about the self anymore. It's about what you can do and how you can be a valuable contributor. People working on the biggest problems are compensated in the biggest ways, not in a strict financial sense, but in a deeply human sense, where it shifts your attention from you to others and the wider world. You stop dwelling, you become less self-absorbed. Ironically, we become happier if we worry less about what makes us happy. So I want to encourage the cognitive computing community to think about societal problems and the big problems and how to develop technology to help people who are out there solving these real-world complex problems. And I'll end it there and open the floor for questions.
Thank you, Steve. That was a great presentation and a really important research. I love technology as a teammate, and I think my Watson colleagues at IBM will like that too. Audience, we have just a couple of minutes. Please press star 1 to unmute your line and ask a question of Steve.
Hi, Steve. My name is Marty. Can you hear me?
Yes, I can hear you. Go ahead, Marty.
I have a research group of about 20 scientists. They have over two-thirds of a million citations to their work. Their focus is how to get very creative in doing what you're talking about. In other words, how not to get boxed in by following a precedent, but how to use it as a stepping stone to bigger pictures. We look at problems where essentially systems of system science, where systems of machines and systems of people interact and so forth. And we're focused on issues of the nexus of very complex problems, such as water, food, energy, and so forth, when they combine to become a major world problem. So I think I have a sort of doing the same thing from a different kind of paradigm, and I'd like to sometime talk with you more about it.
I'll make an introduction. I'll make an introduction to Marty, to Steve, with you, Marty. And Marty's a very important person in this space, Steve. So that would make a great collaboration.
Yeah, that'd be great. And I've seen some really interesting work going on. And just to give an example of how technology supports that from a collaboration standpoint, I've been in discussion with Arizona State University's Decision Theater. And this is a tool that I've been watching for a number of years now, and I think what they're trying to accomplish is important from the standpoint of external cognition and helping people understand problems, but I haven't seen them really focus on the collaboration process. So I think
it's very complicated when you're really
yes.
focusing on
and
of
that's
my
why
individuals, every single individual is in a different discipline. So bringing them together was already a big problem to get going.
Right, and I think the decision theater, this notion of external cognition, is really critical for that, because when you put cognition in the world, that becomes the artifact around which discussion takes place, and it becomes easier for people from different disciplines to realize that, oh, that's really not what I was thinking. They're talking about something completely different, just as a simple example there. Mm-hmm. So, yeah, I'd love to talk more about that.
Wonderful. I'm afraid we're out of time for more questions, but I'll encourage the audience to please go to our LinkedIn discussion group and continue the conversation with Steve. I'll post information about this meeting there. And thank you all for joining. We will see you next week. Thanks a million,
Thank you.
Steve. That was great.
Sure. Thank you. Bye-bye.
Bye.